Okay, so today we are doing systems of inequalities, meaning we're going to be shading two graphs. Specifically, we're doing systems of quadratic inequalities. So we'll graph a parabola, figure out where we would shade, graph the other parabola, see where we would shade, and then we want to see where the two shadings are going to overlap. So they're starting us off slow. They give us this linear function. The graph of y is greater than x plus 1 has been started. So again, to get a linear function, you start with your y-intercept at positive 1, and then it has a slope of 1 where they went up 1, right 1, up 1, right 1, up 1, right 1. They made it a dashed line because it does not have the or equal to. Then it asks us to shade the solution set of the linear inequality. If it's greater than, should we shade above or below? Above. So we're going to shade everything up here. Number 2, the graph of y is less than x squared minus 3 has been started. So again, it's a dashed line because we don't have the or equal to. Whenever you have a quadratic function that doesn't have that middle x term, it doesn't have any movement left or right. So that's why the vertex just went down 3. Shade the solution set of the quadratic inequality. So if it is less than, do we want to shade above or below? Below. So everything outside, because that's below our vertex or below the parabola. Okay, with your partner, identify the shaded regions the two graphs have in common, then discuss what you think the regions that are commonly shaded represent. So the shading for our linear function and where the shading of our parabola, where those are going to overlap, is going to be the solution to our system. You don't have a spot to write that on your paper, though. Okay, third box. The green shading shown is a graph of the solution set. So they have already done that overlap shading for us. So notice how it's above the linear function, but outside or below the parabola. So it's above the line, but below the parabola. So that's why it's only in that gray section, or for me, green section. Okay, number 4, compare the shading you completed in problems 1 and 2 to the solution set. So this is where they're the same graphs. And shading, but this one is only showing where the shading overlaps. You will see me on these systems a lot of times, instead of doing like one color of shading and then a second color of shading, I think that gets a little overwhelming to see like all those colors. I will a lot of times just draw the arrows. Like this is the direction I would shade. And then wherever my arrows are like overlapping or maybe intersecting, that's where I'm going to actually do my final answer of shading. Okay, number 5, discuss with your partner how to use the individual graphs. So the two that we had leading up to this to graph the solution set of the system, summarize your discussion. We've already kind of said it. So the overlap of those two shadings represents the solution set to the system. So we don't call it a solution because there's more than one solution here. It's every single ordered pair that's falling in that shaded area would work for both of those equations, or both those inequalities would be true. Okay, and number 6, they have given us a system. They have already graphed the line and the parabola for us. However, we're expected to do the shading. So our first function is our linear function. So we look at the line. It is greater than. So do I want to shade above or below the line? Above the line. So instead of doing like double shading, I'm just going to draw little arrows to show like what would or where would above the line be. So these are arrows pointing in that direction. So I don't have to keep rethinking of it. I know like that's the direction I would want to go. Okay, then we look at our quadratic. It is y is less than our quadratic. So is that above or below our parabola? Below. So it's going to be on the outside of the parabola. Okay, so our final answer for shading needs to be above the line, but outside the parabola or below the parabola. So that includes everything in here, this little sliver, and then everything out here. Okay, I realize I don't have this on the screen, so give me a second, I'm gonna write it down. Okay, so next in number 7, it says identify whether each point in the table is a solution for each inequality. So when we already have the graph done, we're just looking to see if these points are falling in that shaded area, and if it's the shaded area for both, then it's a solution to the entire system. So the first order pair is -5, 0. That is over here on the left. Go ahead and plot that point and identify it just so we're aware what that point is representing. Would that point be a solution to our linear system? No, it's below the line. That's no good. So you would circle not a solution. Would that point be a solution to the parabola? Like, is that technically outside the parabola? Yes, so that is in the direction where we would have shaded. However, because it's not yes to both or a solution to both, it's technically not a solution to the entire system. Our next order pair, 5, 0. Over here on the right, 5, 0. Now, using the graph that we already have, is that point falling in my shaded area? Yes. So it means that's going to be a solution to my linear function and my quadratic function. So it's above the line and outside or below the parabola. So it works for both. So that would be a solution to the entire system. Okay, then our last point is 0, 10, which is up here at the very top. Is that point technically above the line? Yes, so it is a solution to our linear inequality, but is that point outside or below the parabola? No, so it's not a solution to the quadratic, so it's not a solution to the system. So that's how sometimes I can phrase a question to, like again, so like you're not taking your quest on the computer, and I can't ask you to do something like this on the computer, but could I ask you to say yes or no on the computer? Yes. So that's how these questions can be rephrased, and I would just give you a blank graph. So you would be expected to get a good, solid, accurate graph, and then see where those points are falling. Okay, so again, we've already filled this out. So we said this was not a solution. This was a solution. Solution, 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 not a solution. So I wrote yeses and nos. You would have just circled either solution or not a solution. Number 8, discuss with your partner how the points in the table help to determine the solution set of the following system. So in the last lesson, we did like tester points. So we like plugged it in and we saw like, does that work for the inequality? Yes or no. If it was a yes, we shaded towards that tester point. If it was a no, we shaded away. You can also do the same thing with these problems. So if I wanted to test out, now granted, I know the 0.50 is a solution. We've already done it. But if algebraically, if I'm not trusting my graph, I can prove if it's a solution algebraically just by plugging it in. So my ordered pair 5, 0. So that means I'm going to let x be 5 and y be 0. Okay, so I'm going to start by plugging this new x and y into my linear function. So that would be 0 is greater than or equal to a negative 2 times 5 minus 3. So that would simplify to be 0 is greater than or equal to negative 10 minus 3. Is that a true inequality? Yes. Okay, so that's my way of saying yes, that's a solution to the linear system. Then I can check to see if it would be a solution to the quadratic system. So we would have 0 is less than 5 squared plus 4 times 5 plus 6. If this is also true, it's just validating that we already said it was a solution to our system. So this would be 0 is less than 25 plus 20 plus 6. Is that going to be true? Yes. Okay, so you can also prove solutions algebraically. You don't always have to rely on your graph. So on a test, if you're not confident with your, like, how accurate your graph is, or there's a point that's like borderline, it's kind of close, you can always double check algebraically, like by plugging in. I wouldn't encourage you guys doing it for all the points because that could potentially waste your test time. However, if there was a point that was really close, I would use this just to like make sure you're getting it correct. And when you're ready, flip to the back. Okay, so for these problems, we are given a system. We're asked to generate the graph and do the shading ourselves. So we have two parabolas here because I see this is in standard form. The second one is in factored form. So to start off our first quadratic, we're going to start by finding the x-intercepts. Do we have two numbers that add to equal 6 and multiply to equal 12? Yeah, what are they? Okay, well, there are no x-intercepts. Okay, this is not a factorable one. On a test, I would not ask you to necessarily do the quadratic formula to be super in-depth. I did put this example on here because on the last example or last lesson, we relied on those x-intercepts. I do still want you to know that when you're in standard form, you can use this formula that we've used before, which is x is equal to negative b over 2a. Write that formula down. This is actually just the start of the quadratic formula. So we just plug in, b is that middle number. So it currently is a positive 6. So I'm going to write a negative 6 over 2 times a. A is the number, the coefficient in front of x squared. So that's currently a 1. So this would be 2 times 1. Okay, so this tells me that I'm going to have my vertex falling on negative 3. So that's where my axis of symmetry is going to be. Now to figure out the y coordinate of that spot, we're going to take negative 3 and we're going to plug it back in to that function. So it was x squared, so we're now going to have negative 3 squared plus 6x. So now we're going to have plus 6 times negative 3, and then it's a plus 12. So that's 9 minus 18 plus 12, which is equal to 3. Okay, so when you can't factor a quadratic, that's okay. It's usually faster. I think we're strongest with our factoring skills. Just realize I would not waste your time doing the quadratic formula or completing the square necessarily. I would jump to this quick little formula here. So we're going to plot a point at positive 3. So this makes sense that we don't have any x-intercepts because our vertex is located above the x-axis And because there's this positive x squared here, it's going to open up. So it's already above it and it's opening up, so it's never going to touch the x-axis. We do know that we have this y-intercept with our constant at 12, so we can plot that point. What is the last point we can easily get? Not -4 necessarily. So like this point is 1.5 away from the dashed line, so there's going to be another point 1.5 on the left. So -6, 12. Okay, so that axis of symmetry, I keep putting that dashed line on there so you know any point you have on the left, you're also going to have on the right and vice versa. Almost done with this parabola. Should it be a solid or a dashed line? Dashed. Okay, then it is greater than. Do I want to shade above or below? Above. So I'm just going to draw some arrows to show that I would want to shade above or on the inside of this parabola. I'll do my actual shading once I get my other parabola up there. Okay, now this second quadratic, they have already given it to us in factored form. So we do know that these have x-intercepts. To find those x-intercepts, we can just set each of those factors equal to 0. So what are our two solutions going to be? -6 and 2. I would say this is probably not a step that you necessarily have to write out. So we're at -6 and we're at +2. Okay, to figure out halfway between those two values, we would do -6 plus a negative, or sorry, it's +2. -6 plus 2 divided by 2, that would be a -4/2, which is -2. So this new axis of symmetry is right at -2. So right next to the other axis of symmetry. To figure out where our vertex exactly is, we're going to plug -2 back in. So that would be a -2 plus 6 times a -2 minus 2. So that's 4 times a -4, which is a -16. Okay, so our vertex is at -2, -16. So it's all the way down here. Okay, any questions so far? We're almost done here. Okay, the last just like quick easy point that I want to make sure you know how to find is so that like that y-intercept was kind of helpful because it gives us 2 points actually because I get the reflected point as well. If I FOILed out or multiplied out my constants, what would a +6 times a -2 be? -12. So I have a y-intercept at -12. Okay, so if I multiply my constants together in my factors, that will give me my y-intercept, which means I can also reflect this point across. I would not say that that was super critical, but if you're trying to make your graph as accurate as possible, you want more points on there. And that was just like a quick mental math thing. I wouldn't make you do it if it was like this extensive process. Okay, so will this be solid or dashed? Dashed. And do we want to shade above or below? Above. So it's technically on the inside. Okay, so where do I want to put my final answer of shading? In this small parabola up here. Okay, because that's the area where my shadings would overlap. So the solution to the system is above the blue and above the red. So that's really just falling above the red because the red is inside the blue. Okay, for number 10, we are given a linear system, or sorry, a linear function and a quadratic function. To graph our linear, it's about to be off. This is in the form y equals mx plus b. So where is our y-intercept for this problem? -1. So our y-intercept's at -1. What is our slope? Okay, 3/5. So we'll go up 3, right 5. Up 3, right 5. That was not 5. Instead of going up and to the right, what's the other direction I could go? Down and left. So if I also wanted to just keep it accurate, I could go down 1, 2, 3 and left 1, 2, 3, 4, 5. When I connect these dots, do I want a solid or a dashed line? Dashed. It's just less than. And do I want to shade above this line or below this line? Below, because it says less than. So I'm just going to draw little arrows pointing down to show that that's the direction I would shade. Okay, then our parabola is given to us in factored form. I'm seeing this negative on that -1/4, so I know my parabola is going to open down, and it is in factored form, so I can easily get the x-intercepts by setting x plus 5 equal to 0 and x minus 3 equal to 0. So what are our two x-intercepts? 3 and -5. Okay, what is halfway between -5 and 3? -1. So if I add -5 plus 3 and divide that by 2, that would be a -2/2, which is a -1. So our axis of symmetry, which we show with a dashed line, would go through -1. Okay, now this parabola is going to be a little more complex because it is that -1/4 on the outside. So the negative says it opens down. The 1/4 actually says it's going to be kind of wide. So I'm not going to be super stressed about getting an accurate y-intercept, but I do care about where that vertex is falling. So I'm going to take -1 and I'm going to plug it back in. So we would have a -1/4 times a -1 plus 5 times a -1 minus 3. So -1 plus 5 is 4. -1 minus 3 is a -4. So that would be a -16. What would -1/4 times -16 be? Just a 4. So our vertex is going to be at -1, 4. So on that dashed line, go up to 4 and draw a dot. So I can see I'm going to have a y-intercept. I'm just not exactly sure where it's going to be. And because I would have to multiply by that -1/4, it's likely going to be a decimal or a fraction, and that's not going to be a perfect, accurate spot anyway, so that's why I don't want to waste my time. Do I want this parabola to be solid or dashed? Solid. And do I want to shade above or below the parabola? Below. So that would be on the inside or the outside? The inside. Okay, so where is my shading going to overlap? Inside the parabola, but below the line. So everything right here. Okay, third graph on here, we are given two quadratics, so we're going to have two parabolas. The first parabola, the top one, I'm going to think, could I factor that? So if I took out a -1, we would have x squared minus 4x plus 3. Do I have two numbers that add to equal -4 and multiply to be 3, a positive 3? Yeah, what are they? So when I took out a -1, it flipped all the signs. Because you're in front of the x squared, it has to be a positive 1 before you can factor. So you took out a GCF of -1 first. Okay, but yeah, you have one at -3 and -1. Okay, so we have x minus 1 times x minus 3. So where are our two x-intercepts? 3 and 1. Okay, this one's kind of nice. They're close together. What has to be our halfway spot? 2. So you don't have to do that adding and dividing by 2 thing if you can just see the halfway spot. However, don't let that, like, if you're not sure where halfway is, use the math to actually find it. Okay, to find our vertex, we're going to take that value of 2 and we're going to plug it in. So it would be a -2 squared plus 4 times 2 minus 3. So that would be a -4 plus 8 minus 3, which would just be 1. Okay, last easy point for this parabola. We have our y-intercept at our constant. So we'll have our y-intercept down here at -3. So the constant of -3 tells us our y-intercept, and then we can reflect that point across to get another value for -3. I think at this point we can see our parabola. It's pretty accurate. Do I want to make this parabola have a solid or a dashed line? Solid. And would I want to shade above or below this parabola? Below, it's less than. So it's everything on the inside of the parabola. Okay, for our second parabola, I see that we have this -x squared, so it's going to open down. Is this factorable? So if I took out like a -1, can we factor x squared plus 8? Is that the difference of squares pattern? No, it's difference means I'm subtracting. Squares means I can square root both of them. So there are no x-intercepts. because I'm not going to be mean to you and give you irrational x-intercepts for this unit. That's not the point. So we're stuck using our formula x equals a negative b over 2a. What is my b in this problem? 0. I don't have a middle term, so it's a 0. What is 0 divided by anything? 0. So it doesn't matter what 2a is, we're going to get 0. So our axis of symmetry is falling on the y-axis. Then if I plug in 0 back into this function, we would have a negative 0 squared minus 8. So what do we get? Negative 8. Okay, so our vertex is the y-intercept, sorry. Okay, so this makes sense that we did not get any x-intercepts because we're below the x-axis and we know it opens down. So it's never going to reach the x-axis. Are we ready to see if we can remember something that I said like a month or two ago? Okay, do we remember the day that I said, what are odd numbers? Okay, what are some examples of odd numbers? 1, 3, 5, 7, 9. Okay, do I go up 1? Okay, but my problem is opening down this time. So for every time I count either left or right, I'm going to go down 1. Then the next time I go left or right, I'll go down 3. So it counts by odd numbers. So the first time I go to the right one, I'll go down 1. I'll also have the point on the left side that's also down 1, left 1. Okay, after 1, what is my next odd number? 3. So I'll still go either left or right, but now I'm going to go down 3 this time. Now my next odd number would be a 5. Why does it not make sense for me to do that? It's off the graph. So that's a helpful trick that only works if that leading term is a 1 or a negative 1. So if you checked your blue parabola, the one we already have, we went down 1, right 1, down 3, right 1. I bet if we went down 1, 2, 3, 4, 5, right 1. So it still matches up. The next one would be down 7, right 1. So I think that's maybe where my graph isn't super accurate. So we technically could have used that trick on the top one. I don't want you always to rely on it because that negative 1/4 quadratic we had in the last problem, it would not have worked for that one. So your other skills are more reliable. However, if you have a 1 or a negative 1 in front of the x squared, you can just do that 1, 3, 5, 7 thing. This second parabola, solid or dashed? Solid. And do I want to shade above or below this parabola? Okay, it's greater than, so I want to shade above. So it's on the outside. So where is my final solution going to be? Perfect. Below the first one, above the second one. Okay, for this last question, we have our friend Hope attempted to graph a solution set to the system of inequalities. So she has two quadratics or two parabolas graphed, which makes sense because we have these 2x squareds. Talk with your group, see if you can figure out the mistake that Hope made, and how her graph would be different if she corrected her mistake. So see if you can find where she went wrong. Okay, so what mistake did Hope make? There are two. Okay, so this first one should be dashed. Dashed or dotted, however you want to say it. Okay, so the first inequality should be dashed. Okay, what is the second mistake that she made? Her parabolas are in the right spot. So if it's not an issue with where she put the parabolas and the lines are good, she shaded it wrong. Which one is shaded wrong, the blue or the black? No, we're not sure. Okay, so think. The black line is the very first equation. No, sorry, the blue is the first equation. If it is less than, is that above or below? Below. So the shading on the blue is good. Okay, for the black equation, it is greater than. So that should be above the black equation. It's currently below. So then we can also mention the shading on the second should be above. Okay, so if we know her parabolas are correct, so it looks something like this. That's a terrible little sketch. We want to be above the black, but below the blue, so our shading would just be in the middle here. I would say that if they give you a system problem and they're asking for the error, it's likely dealing with the lines and the solid or the dashed. And then I would always double check the shading. I would say it's rare if they actually made a mistake on the movement of like where they place the parabolas, because again, this lesson is about the shading and the dashed or solid lines. So she should have shaded it in between the two. So you can either make a little sketch or just make a note that that's where the shading should have been.